Hello all, welcome to this session on homomorphic encryption. Uh, Myself Disha Anand and I'm currently doing my engineering third year in VIT Chennai. So let's get started. Before coming to talk about what is meant by homomorphic encryption, let's understand what is encryption. It is a process of converting the plain text data into ciphertext data to protect the confidentiality. Let's keep it simple. Let's say myself Disha and I'm sending a message to Bob, and if I'm going to send the message, let's say the message is hi Bob. If I'm going to send that message without encrypting it, a middleman will be able to read what message I'm sending. In case if I'm going to encrypt it as hi as BI and Bob as let's say EOE. Now here the middleman will not be able to understand what I'm exactly trying to send, but when the message reaches Bob, it will get decrypted and he'll be able to read the message. This is the process of encryption. So some of the examples of encryption algorithm are AES algorithm, RSA algorithm, and we have DES. And the algorithm which we are going to see, homomorphic encryption, all these are examples of uh, encryption algorithms. And let's come to the need of secured computation. Now, before understanding the need of secured computation, let's try to understand why we are going to analyze the need of secured computation here. How is it related? So, homomorphic encryption is an algorithm which is being done on cloud. So, let's say I'm going to carry out a data analysis or I'm going to train a machine learning model. I'll be working with the data, so that data might be confidential and the person might not be comfortable with seeing the data. The customer might not be comfortable with me seeing the data. In that case, we use homomorphic encryption where the process or the computation will be carried out in the encrypted data only. So the need here is we store and process massive amount of data in cloud. Traditional encryption protects data only when stored or transmitted. So only when I'm going to store the data will be encrypted, and when I'm going to transmit the data to someone else, there the data gets encrypted. But when the actual computation is done, the data gets decrypted. So this is a drawback of traditional encryption. So to compensate this drawback, the homomorphic encryption has come into play where we can process the data without decrypting it. So the data and the computation will be carried out on the encrypted data. Now, let's understand what is homomorphic encryption. Homomorphic encryption is a special kind of encryption that allows the computation directly on the encrypted data. As I said earlier, all the operation and the computation are being carried out in the encrypted data only without the analyst or the data scientist actually seeing the data. And when the final result is obtained, only the final encrypted will be decrypted and the scientist or the analyst will be able to see the data. So to understand this entire process, there is a one line crisp explanation over here. The computation as being done in the encrypted data, and finally that will be decrypted, and this will be equal to the computed data, that is the final answer. Now let's understand how it works. You send the encrypted data to the cloud, and in cloud the computation is being carried out in the encrypted data only, and when we get the results back, we decrypt the data locally and it is exactly same as the result you would have if the computation is done in the decrypted data. That is, the data will be encrypted using the public key, and the server performs the computation on the ciphertext, and then the decryption is done, and then the decrypted result will be identical to what we get if the operation is done on the plain text. This is how it works. Now let's come to the types of homomorphic encryption. We have partially homomorphic encryption, somewhat homomorphic encryption, fully homomorphic encryption. In partially homomorphic encryption, only one addition or multiplication can be done, whereas in somewhat homomorphic and fully homomorphic, two operations can be done. But the difference between SHE and FHE is, here in SHE, the number of operations is limited, while in the FHE we have unlimited operation. Now let's come to the example. Here we are taking a simple example. Now we have two prime numbers 5 and 7. And here, to prove this, we want to prove that if the addition of two encrypted number, that result when decrypted will give the sum of the original number. So in step 1, the key generation, in PAL here, we choose two prime numbers, say 3 and 5. Multiplying them gives us n, that is 15. Now the public key is based on n and g, that is n plus 1. Well, the private key uses special mathematical values derived from these primes. In real life, these numbers are very huge. Here we are using small ones to make the math easy for us. Next, we encrypt our two messages. Let's say 5 and 4. The encryption formula involves exponentiation and random value to keep it secure. After computing, we get the encrypted number, which we'll call it as E of 5 and E of 7. And now comes the magic. Instead of decrypting them, we multiply the encrypted numbers. In parallel encryption, multiplying the cipher text corresponds to adding their prime values. When we multiply E of 5 and E of 7, we get new encrypted that actually represents E of 12. Finally, when we decrypt that result, the answer is 12. That is exactly the same match of the original number. At no point did we ever decrypt 5 or 7 during the process. This demonstrates that the additive homomorphism, meaning the addition of plain text, would correspond to the multiplication of the encrypted word. In this way, the server can perform computation on the encrypted data without even seeing the real value. Now coming to the application, this is the major part. Where are we using this homomorphic encryption? In healthcare. So hospitals are not supposed to share the patient's crucial data or the private data. In that case, for the analyst or the data scientist to carry out their operation, they can use this homomorphic encryption. And in finance, the banks perform fraud detection. So with this, we can use the encrypted transaction. In government sectors, we can use where private privacy preserving census and election analytics. Here we can use it. Then in machine learning, we can use it for training model on encrypted data where privacy preservation is a major concern. Then we can use it in IoT. Devices can send encrypted sensors data to the cloud, and there the computation can be performed. So these are the various applications of homomorphic encryption. So this is the mathematical idea behind the homomorphic encryption. That is, in the additive homomorphic, uh, E of A plus E of B gives us E of A plus B, and multiplication gives us E of A into B. That is nothing but, as I explained in the earlier example, we get the same values. So that is what reflected here in the mathematical form. Let's see how it's different from other privacy techniques. So in data masking, what it does is it hides the sensitive information, but it is irreversible. So since it's not irreversible, it's not secured enough. So in encryption process protects at rest or in transit only, that is only when it is stored or when we are sending the file. So here we have to undergo decryption process, and in differential privacy, the result will be added with the noise. So thus the accuracy gets affected. So when the noise is added, it means there might be the presence of outliers or extreme values. So thus it reduces the accuracy. But in homomorphic encryption, the process is done in the encrypted data directly. Here the limitation is that it is computationally heavy. The computation is difficult. Also the processing time is very huge here. So we need a high GPU system. So these are the limitations of using homomorphic encryption. Now, coming to performance and optimization. So here, in early FHE schemes were millions of times slower than normal computation. Modern techniques BFV, CKKS reduces the cost drastically, and hardware acceleration using GPU, FPGA has its value. And also parallel computation has also increased the performance here. And now the famous cloud platforms like Microsoft Azure, IBM Cloud are also experimenting with the FHE. That is, here when we talk about the performance and optimization, performance has always been a very big bottleneck for homomorphic encryption. So in the year 2009, computation that took milliseconds on the plain text took hours in the homomorphic encryption algorithm. So now, by using the new algorithms like CFFS, BFE, it makes the real-time encrypted inference possible. And also, companies like IBM, Microsoft, Google are investing heavily in specialized hardware and the optimized library to make this FHE usable in the normal scale. Now, here we are going to see about integration with AI and cloud. So, here combining FHA with federated learning. So, federated learning is nothing but a process where we send the model to individual system and it is trained to the data present in that model. That is, let's say I will send a model to my system, and with the data in my system the model will get trained. That is called as federated learning. So now research are going on with combining this algorithm with the federated learning in order to have a privacy preserving AI system. Then use in secure data outstanding for healthcare and finance. As I said earlier, healthcare fields, when the experiments are carried out in healthcare fields, the data outsourcing becomes a very big problem. So let's say now we are in need of doing some early base deduction for Huntington disease, which is a very rare disease and also it's intreatable disease. But the limitation to carry out that particular research was that the people with Huntington's disease are very less in number, and also people who are affected by that disease, their families are not willing to share the data because of the privacy concerns. When this algorithm like FHE algorithm, if they come into real life working scenario, then computer based solutions can be built for such incurable disease. So thus it is very important in terms of healthcare and finance sector. And also it enables encrypted machine learning inference. So in case as I said, for the data which has like high privacy concern, so let's say we have like image recognition system and some other sensitive data related data set for carrying out the machine learning algorithm. There this privacy becomes a very major issues, and that has become a fundamental reason where many diseases and many genetic problems, they don't have computer based detection system. So this algorithm will be a turning point for all this, and also cloud providers can process encrypted customer data without seeing it. So this can be used for customer data as well. And also now researchers are standardizing the FHE protocols and the API, so that the developers can integrate them easily with this AI, this platforms. So because it is built on lattice cryptography, it is believed to be in quantum safe, meaning that even if future quantum computers can easily break it. So we are also seeing hybrid system that combines FHE with blockchain to ensure transparency and immutability. In future, we might be able to even compute securely in cloud as naturally as we browse in web today. So these are the future we see with this FHE algorithm. Um, yeah, that's about the research point of view, which I said now. And yeah, that's it. Now let's start with limitations and challenges. It's useful. Thank you.